Hello guys, welcome back to the channel. In our previous video, we tackled the indefinite integrals and the U substitution. Today, we are going to explore definite integrals, a cornerstone of calculus that helps us calculate areas, total changes, and so much more. We will break down the progress step by step from understanding the limit of integration to applying techniques like U sub in a definite integral context. So get ready to deepen your understanding and see how definite integrals bring math to life. So the basic difference between the definite and indefinite integral is just the upper and lower limit that we have in this case. So now let's tackle this. Now to solve this problem, as we did before, whenever you have something with an exponent, we choose that to be our u. So in this case, we have the u to be equal to the secant of x, right? We ignore the square. In this case, if we differentiate u with respect to x, we get secant of x tangent of x, right? Okay, now let's try to find the x. The x will be equal to the u out of secant of x tangent of x. So we have to go back and try to see if this is going to work. Now if we have x is equal to 0, if x is equal to 0, that is the 0 right here, we are going to have u. Now remember, whenever you have a definite integral, you have to change the upper and lower bounds. Now this is because the 0 and pi over 4 over here corresponds to that of x. But in this case, since we are changing everything to u, we have to have an upper and lower limit for u, right? So if x is equal to u, we have to find secant of 0. And secant, remember, is 1 out of cosine. So we have 1 out of cos 0, and this is 1 out of 1. Okay, now when x is equal to pi over 4, we have our u to be equal to sec of pi out of 4, and that is 1 over cosine of pi out of 4. But we know cos of pi out of 4 is root 2 out of 2. So you have to simplify 1 over root 2 out of 2. So 1 dividing root 2 out of 2 will just simply be root 2. So in this case, we have root 2 here. So what this means is you have from 0 to pi over 4, and from 0 we had 1 over here, and we now have root 2 here, right? We have tan of x here, and we said we have sec x to be our u, so we have over here to be u squared, and the x we have the u out of sec x multiplying tan x. So we get to see that this over here cancels this, right? So this expression is the same as writing 1 multiplying the root 2 out of we have u squared du out of sec x. So now you have to ask yourself this question: how do you solve this question? Because in this case, we are integrating with respect to u, and you have sec x also over here. So solving this problem becomes very tedious, meaning that the u that we selected over here was a problem. So in that case, you have to select another u. So let's see. So it means this process does not work, right? So that's what I'm saying, that it's always try and test, right? So let's say we select u to now be tan of x. In that case, if we differentiate u with respect to x, we have secant, we have secant square root of x, and in that case the x is now equal to the u out of the secant square root of x. So if x is equal to 0, we are going to have u to be equal to the tangent, we're going to have u to the tangent of 0. And what is tangent of 0? Remember, tangent is sine over cosine. So sine of 0 is just 0, and cosine of 0 is 1. So in that case, we have 0 right here. Now, when x is equal to that upper limit, which is pi over 4, we have u to be equal to tangent of pi over 4. So in this case, we have sine of pi over 4, and we have cosine of pi over 4. So sine of pi over 4, as we know already, is root 2 out of 2, and cosine of pi over 4 is the same thing, which is root 2 out of 2. So this cancels out each other, so we have 1. So in this case, when x is 0, we had 0 as well, so we have 0 over here, and when x is pi over 4, we had 1, so we have 1 here. Now tan x is now our u, and we have secant squared x. Now the x, we had the u out of secant squared of x. So you see, in that case, this cancels out this, and you're just going to have from 0 to 1 u of the u left. So you see, over here, there is nothing like x over here. So it becomes very easy to integrate. So that's why your selection of u is very critical. So in this case, if we integrate u, we have u squared over 2. But note, this is definite, so we don't add any constant. We don't bring any plus c. So the next thing is to sub in our 1 and 0. So we have 1 squared out of 2 minus 0 squared out of 2. And this just simplifies to 1 out of 2. I hope this is clear. Okay, let's look at a different question. We have from 0 to pi of 3 cos squared of x sine of x dx. So in this case, we can rewrite the expression. We can have the constant outside, then from 0 to pi cos squared of x sine of x dx. So in this case, which one do we choose as our u, right? So going back to this, you see we had the squared, we selected u to be sec x, we solved and we didn't have any problem. In this case, this is funny, right? Because in this case, let's try and see if we select cosine of x, right? A normal idea is if we select sine of x, right, it should follow this pattern. But now let's go ahead and select cosine of x. If we select cosine of x and we differentiate, we have the u, the x. This is going to be, remember, if we differentiate cosine, you have minus sine of x. So in that case, here the x is just minus, it's just minus the u out of sine of x. So let's rewrite our expression. We're going to have 3. Before we do that, let's change our bounds. So when x is equal to 0, we are going to have u equal to cosine of 0, and cosine of 0 is 1. And when x is equal to pi, we're going to have u to be equal to cosine of pi, but cosine of pi is negative 1. So if we rewrite the expression, we are going to have 3, and when x is equal to 0, we had 1. When x is equal to pi, we had minus 1. Then cos squared s means we have u squared. And then we have sine of x multiplying minus du out of sine of x. So clearly over here sine of x cancels out sine of x. So we are going to have, so this is equal to, remember this lower bound should be lesser than this, but in this case that's not the case. So what we have to do is to interchange the bounds. And remember from our previous video, if we're interchanging bounds, we bring negative in front. So we have now negative 1 and 1. Then we have minus u squared du. So we can also bring this negative outside, and if it goes outside it cancels the negative in front of 3. So we have positive 3, negative 1 to 1, then u squared du. So now we have 3, and if we integrate u squared, we have u cubed out of 3. Then we bring our lower and upper bounds. So 3 cancels out 3 over here. So we just have u cubed, right? So this is 1. So we put inside 1 to the power of 3. Then remember, from fundamental theorem of calculus part 2, we subtract always. Then we bring negative 1 to the exponent of 3. And 1 to the exponent of 3 is 1. Then minus negative 1 to the exponent of 3 is minus 1. So 1 minus minus 1 is positive 2. And this is our answer. You can also try to select sine of x to see if it's going to work. Okay, let's move on to the third question. For the third question, we have the integral of negative 1 to 1. We have 5r. We have 4 plus r squared or squared r. In this case, let's select our u to be equal to what is inside the parenthesis, which is 4 plus r squared. So if we differentiate u with respect to r, we have just 2r here. In that case, our dr is just du out of 2r. Now let's try to change the bounds as well. In changing the bounds, when s is equal to positive 1, our u will be equal to 4 plus 1 squared, and this is just 4 plus 1, which is equal to 5. And when s is equal to negative 1, we have u to be equal to 4 plus negative 1 squared, and that is also 4 plus 1, and this is equal to 5. So you see there is a problem, right? Let's rewrite this. In this case, we have lower and upper bound to be the same, and we have 5r over, now we have u squared. The r was just the u out of 2r. Though this and this cancels out, you can rewrite this again. Let's just try to see. So if we have 5 over 2 outside, and we have integral of 5 to 5 the u out of u squared. Can you tell me where the problem is? Do you remember? Note that from our previous videos, since the upper bound and lower bounds are the same, if you simplify, you end up getting 0. So this just goes to 0. So it means that if we integrate this expression right here, we get 0. Okay, now let's look at our last question. We have from 0 to pi over 4. We have 1 plus e to the exponent of tan theta and secant squared theta d theta. Okay, now remember from our previous examples that I say whenever you have an expression with an exponent, you always make the exponential u. So in that case, we are going to have our u to be equal to tangent of theta, and if you differentiate u with respect to theta, remember you get secant squared theta. So in that case, if you want to find the theta is just the u over secant squared theta, and we change our bounds. So now when x is equal to pi over 4, we have to have u to be equal to tan of pi over 4, and remember we've done that already. over here. That's what we did here. Tan pi over 4 and tan of 0. So for tan of pi over 4, we had 1. So in this case, this is equal to 1. And when x is equal to 0, we have u to be equal to tan of 0, and this is also equal to 0. So let's rewrite it. If we do, we have 0 to 1, then 1 plus e exponent tan of theta, but tan of theta is now our u, so we have e to the u secant squared theta. And now the theta, we had this, so we have the u out of secant squared theta. So this cancels out this. So we just have integral of 0 to 1 plus e to the exponent of u du. So now let's go ahead to integrate. Remember, if you integrate a constant, you get a variable that you are integrating with respect to. So in that case, we have just u over here. And if you integrate e to the exponent of u, you have the same thing. Then our lower and upper limit. So we just sub in our upper limit first. So we just have 1 plus e to the u, which is now 1. Then minus, we sub in our 0, so we have 0 plus e to the 0. So this simplifies to 1 plus, now e to the exponent of 1 is just e, minus 0, minus, now e to the exponent of 0 is 1. So you see 1 minus 1 cancels out, so this cancels out this. So you just have e minus 0, which is just e. So I hope this is clear. That wraps up our introduction to definite integrals. I hope you are feeling more confident in evaluating them and understanding how they connect to real-world applications. If this video helped you, as always, be sure to like, share, and subscribe for more math tutorials. And don't forget to comment below with any questions or suggestions for future topics. Thanks for tuning in, and I'll see you in the next video. Keep pushing forward and enjoy the beauty of calculus. To mention, this is our last video of the series. The next video I'm going to upload is going to be a test, more or less like an exam or a final for us to solve together. I'll see you.